viewers. In today's lecture, we are going to study asynchronous up counter. So let's get started. Have you ever wondered how digital clocks work? This is where counters come to play. A digital clock is constructed using cascade of 6 asynchronous falling edge triggered BCD counters. Counters are one of the simplest type of sequential circuits. Counters are constructed from flip-flops that change state in a prescribed sequence when input pulses are received. Clock-driven counters can be used to count the number of clock pulses. Since clock pulses occur at a certain time intervals, hence they are used to measure time and period of frequency. Counters are broadly classified as asynchronous counters, synchronous counters, single counters and multimode counters, and modulus counters. The simplest counter circuit can be made from the T flip-flop due to its toggle feature, which is suitable for the counting operation. They can also be made using JK flip-flops. Asynchronous counters are of 3 types: asynchronous up counter, asynchronous down counter, and asynchronous up-down counter. Here we will mainly focus on asynchronous up counter. The following counter is capable of counting from 0 to 7. Then clock inputs of the 3 flip-flops are connected in a cascade. The 3 input of each flip-flop is connected to a fixed one. This means that the state of the counter will toggle at each negative edge of the clock. Assuming that the purpose of this counter is to count the numbers of pulses occurring at primary input, therefore the clock input of the first flip-flop is connected to the clock line, whereas the clock inputs of the corresponding flip-flops are the outputs of the preceding flip-flops. Hence, they toggle their state whenever the preceding flip-flop changes its state from Q is equal to 1 to Q is equal to 0, resulting in a negative edge of the Q signal. In the given timing diagram, the value of Q0 toggles at every negative edge of the clock signal. Now, since the second flip-flop is clocked with Q0, the value of Q1 toggles at every negative edge of the Q0 signal. Similarly, since the third flip-flop is clocked with Q1, the value of Q2 toggles at every negative edge of the Q1 signal. Looking carefully at the values of Q2, Q1, Q0 as the count, the timing diagram indicates that the sequence is in 0, 1, 2, 3, 4, 5, 6, 7 and again 0, 1, 2 fashion. As it counts in upward direction, it is known as up counter. Only the first stage of flip-flop responds directly to the clock signal, but the remaining flip-flops respond after an additional delay. The following truth table shows the sequence of n binary states that the flip-flop follows that we have discussed earlier. The figure shows the 3-bit binary ripple counter with the decoded outputs. This is the same circuit only with the additional decoding circuitry. The counter shown has 8 different states. Hence, it is a mod 8 asynchronous counter. The modulus of a counter is total number of unique states it passes through each complete cycle. Modulus is equal to 2 to the power n, where n is the number of flip-flops. The maximum binary number that can be counted by the counter is 2 to the power n minus 1. Let us consider the counter. The input consists of a sequence of pulses of frequency f. Q0 changes from 0 to 1 in first negative transition of the clock cycle, and Q0 changes from 1 to 0 in the second negative transition of the clock cycle. Hence, 2 input pulses will result in a single pulse in Q0. Thus, the frequency of Q0 is f by 2. Similarly, the frequency of Q1 will be half of the frequency of Q0, that is f by 4. In the similar fashion, the frequency of Q2 will be half of the frequency of Q1, that is f by 8. As these circuits is used to divide the input frequency, thus they are named as frequency dividers. In today's lecture, we have learned introduction to different types of counters, asynchronous up counter, mod number of counter, frequency division. With this, we are at the end of this lecture. We will meet again in the next lecture. Till then, learn and practice. Thank you and goodbye.